So welcome back for our discussion on unsteady viscous flows. So in the previous lecture, we have been looking at different kinds of problems where unsteady diffusion was being considered. So we looked at a problem where you have an impulsively pulled plate and looking at how momentum diffuses from that impulsively pulled plate. We also saw the configuration where instead of there being a single plate, there are two plates. So the top plate is held stationary and the bottom plate is impulsively set into motion. And now we know what we would get in steady state. We know that this is going to actually be a linear problem, which is our plane co-ed flow problem. What the unsteady analysis showed us that the attainment of the linear problem happens through a sequence of these, or the linear velocity problem, because the governing equation is always linear. We are not solving any nonlinear equation. So the linear velocity profile is achieved as the steady state solution of the unsteady problem. And we also understood that what does it mean when we say that we are going to achieve steady state. I mean, mathematically, obviously, you push t going to infinity and you will achieve the steady state solution, which is the axial, the horizontal velocity is u bar 1 minus y by h, because whatever are the unsteady terms, they are going to go to 0 as t goes to infinity. But the more appropriate way of thinking of this problem is to think of this as the scenario where t divided by a viscous time scale, which is h square by nu, this approaches infinity. Rather than saying that the dimensional time approaches infinity, it is more important to actually think in terms of that there is a non-dimensional time where time much larger than a viscous diffusion time scale given by the width of the two plates is when you are going to achieve or look at steady state. So I have been using again small h, so let me just correct that. So t divided by h square by nu. So this gives you some perspective, because if you think in terms of a fluid and you say I consider a water-like medium, so kinematic viscosity of water would be around 10 to the power minus 6 meters square per second. And now if you say that I have a plate gap which is around a millimeter, which is 10 to the power 3 meter, then you can see that this quantity h square by nu is approximately 1 second. So it tells you that when you are doing this as an experiment or you are doing this in a simulation, if you try doing this problem, that you move one of the plates and you ask how long should I wait for us to observe a linear velocity profile, here is your answer. That the time scale over which you should observe in order to see that linear velocity profile should be larger than 1 second here. Now you can play with this. You can now increase the gap and make it few centimeters in size, and then you will get this to be of the order of few minutes. So this gives you a perspective of what is infinite, because mathematically you can obviously put t equal to infinity and say that's the steady state. But physically, when you are doing this in a numerical simulation, you set this up and you are saying that how long should I wait before I should see the co-ed flow profile. That's a normal question which we will always ask. Usually you will do some unsteady simulations and then you are asking that do I wait in terms of dimensional time units few seconds, do I wait few minutes, do I wait few hours. So the answer lies here that you need to wait for time intervals which are larger than the characteristic dimension h square by nu. And this is applicable for a large variety of problems. Like instead of it being an internal flow, if you had an external flow where you did some unsteady effects and you are asking that how long should you wait for steady state to be attained, and let's say this is the typical size of the object, you automatically arrive at a viscous time scale which is a square by nu. And if you are observing the dynamics on time scale much larger than this, you should see a steady state problem. This is with a big caveat that whatever you are doing here is within the assumed condition of unidirectional fully developed flows. We have already discussed this before, that you will see transition in these problems to more disordered state, more turbulent like states, and then eventually a turbulent state. So obviously all of these things are not necessarily going to get carried over there. So at least if you are staying in a regime where the flow is nice and laminar, this is a nice recipe to work with. That look at a problem and ask that if you are doing this as an initial value problem, there is a time scale which fixes when all the unsteady effects are going to get equilibrated in the problem. So that was a problem where you had a time scale that was given by the dimension of the problem, which was h. So h square by nu gave us a time scale, and which is how we worked this problem out. Today we are going to look at a problem where we will revisit the infinite plate problem, but the plate, instead of actually moving with a constant velocity, is now doing an oscillatory motion. So I will draw my coordinate system y, x. Our equations do not change. So it is dou u dou t nu dou square u dou y square. The boundary condition is that u at y equals 0 for all time is u bar cos omega t. And the other boundary condition is u as y approaches infinity for all time will be 0, which means the fluid velocity decays off to 0 at infinity and it equates to the plate velocity at the location of the plate. That is basically a no slip boundary condition. Now this is an initial value problem, so you also need an initial condition. So the initial condition would be that the velocity everywhere, I am putting y plus here because there is a discontinuity at exactly at y equals 0. So for any positive value of y at t equals 0, the fluid velocity is equal to 0. It's the same set of boundary and initial conditions that we had earlier. Now again, there are various methods of solving this problem in an exact manner with all that is given. But let's maybe just take help of dimensional analysis in the beginning to see that what can we already anticipate before we do a complete calculation. So once again, if you see that there is a velocity u bar that is here, which is the plate velocity's magnitude of oscillation. If you increase this by a factor of c, then the entire problem will increase by a factor of c. If instead of u bar, if you have c u bar, then whatever was the solution for c equals to 1 needs to be multiplied by that scalar factor. This is just basically invoking the idea of linearity of equation and linearity of boundary condition. So that tells us that u by u bar is a function of y, t, nu and omega. There is no x in the problem, because if you do a classical dimensional analysis for this, dimensional analysis will tell you that there is u is a function of u bar, y, t, nu and omega. This is what, not knowing anything about the problem, this is what you would have started out with. Going from here to here, we have exploited the fact that we are dealing with a linear problem. So linearity tells us that the dependence on u bar is linear. Now the left hand side is non-dimensional, so the right hand side also should be non-dimensional. So now you can construct the dimensionless groups in the problem. So here there is one dimensionless group which is y by 2 root nu t, which we have already worked out as a solution. Now the other dimensionless group, you could either write it as omega t, or, so I am giving all possible combinations. So you can write it as a function f1 of these quantities, or you can write it as a function f of y by 2 root nu t, y by omega by nu. You can see their linear combination, or you can write it as y omega by nu omega t. You can do all of these combinations. They are not any different. I mean, finally, you only have there are 3 non-dimensional quantities in the problem. If you do a pi group calculation, you have 1, 2, 3, 4, 5, 6. There are 6 parameters or dimensional variables. If you use an MLT system, you are going to land up with 3 pi groups in this problem. And one of the pi groups I have fixed it as u by u bar. So, automatically the other 2 pi groups would come out of combinations like this. So, you can expect one of these is how the solution form should be. So, that tells us that expecting a similarity solution here is not going to work out. There will not be a perfect similarity because you have an inherent time scale. So, there is an intrinsic, not intrinsic actually, there is an imposed time scale in this problem, which is omega inverse. Omega is the frequency of oscillation. So, that automatically imposes a time scale in the problem. Now, as I was mentioning, you can solve this problem by considering different methods. One method would be you do a Laplace transform, and after doing a Laplace transform, you reduce this initial value problem into a boundary value problem in the variable y, solve it in y, apply the boundary condition and then do an inverse Laplace transform. Now, we expect, like you can think in terms of what do you expect in this scenario. So, go back to what you know about a classical oscillator problem. So, classical oscillator problem is like you have a mass, you have a spring, and you can probably also have a damping that is there in the problem. Now, here when you write down this equation, you will write mx double dot cx dot plus kx is equal to with some forcing. So, you apply some forcing on this problem, and let us say the forcing is harmonic forcing, some oscillatory forcing. So, it is a forced harmonic oscillator. Now, what do you see in this particular problem? You will see initially there is going to be a response that will depend on your initial conditions, and if you wait long enough, the response of this oscillator would be some function of this kind. So, this is some constant times, let us say, cos omega t. So, for the oscillator problem, if you wait long enough, all your transients are going to go away, and then the oscillator is going to latch on to whatever is your forcing frequency. Obviously, these constants will have information regarding the damping, mass, stiffness, etc. all that will be there, but finally, you are forcing it with some frequency, the system is going to die down. There is going to be a decay of its response because there is a damping in the problem. The response is going to die down, and then response as in like the transients will die down. So, whatever is the information regarding your initial condition will go away, and finally, you will achieve this kind of an equilibrium state where it is undergoing an oscillatory behavior. So, we are going to do the same thing here. We are not going to focus on transients. So, we will ignore the transients here. In the previous problem, we actually worked out the transients in detail. Here also you can do it, but we will right now not focus on the transients. So, we are going to look at the solution at large time, and you already have a feel of what do you mean by large here. Okay. So, what I will say here is I want to solve this equation, and I will assume that u is some function of y e to the power I omega t. Why did I put a real here? I added a real part here because working with an exponential is easier. I could have written, so this is basically the assumed form of the solution that I have, that f can be complex, this is complex, and finally the real part of that is the solution. You have a differential equation here which has a forcing where the boundary condition is u at y equals 0 for all time is u bar cos omega t, right? So this, what do I write this as? I can write this as the real part of u bar e to the power I omega t. It's the same language, right? It's just writing it in that form, because when you take a derivative of a sine or a cosine, you get the other one. So you have to keep track of that phase change that you have every time you do a differentiation. Whereas when you treat it with an exponential, you always obviously have that phase, but the functional form remains the same. So the exponential will remain an exponential, so it's easy to do the algebra. That's the reason why you are making this kind of an answer. You could say that it is some f of y cos omega t plus g of y sin omega t, and then work everything out and find out what the solution is. This is just going to be significantly more efficient in terms of doing the calculation. The other boundary condition is u as y goes to infinity for all time will be quiescent. So I am not interested in a problem that has anything to do with initial conditions. So assuming all transients go away. So if I substitute it into that problem, I will get I omega f is equal to, so there is an e to the power I omega t here, nu e to the power I omega t d square f dy square. Now you can see that the exponentials are going to vanish off. This will be applicable for all time. So I can cancel out the exponential and I get a differential equation which is d square f dy square minus I omega by nu f is equal to 0. So by assuming this particular form, what I am solving for now turns out to be a reasonably simple equation. And what should be f at the two boundaries? What should be f at infinity? F is only a function of y. So f as y goes to infinity should be equal to 0. And f at y equals 0 should be equal to u bar. So you just have to now deal with a second order differential equation. Okay. So now what I will do, I will write this as d square f dy square plus alpha square f is equal to 0, where alpha square is minus I omega by nu. So this has solution f of y will be some constant a exponential of alpha y plus some constant b exponential of minus alpha y. Now if you check alpha, alpha is square root of minus I omega by nu. Now how do I do the square root? Now minus I is minus e to the power I pi by 2, right? Everyone agrees with this, right? I is basically e to the power I pi by 2. Now there is a minus here. I can write this as e to the power I pi, e to the power I pi by 2, because minus 1 is e to the power I pi. So then this becomes e to the power I 3 pi by 2. Okay. So then this is square root of omega by nu e to the power I 3 pi by 2. Which is square root of omega by nu e to the power I 3 pi by 4. So alpha is square root omega by nu cos 3 pi by 4 plus I sin 3 pi by 4. Now, what is cos 3 pi by 4? So, this should be 1 by root 2, I by root 2. Is that okay? So, my alpha is omega by 2 nu into 1 plus I. Now, the reason for doing all of this is to check what is the real part of alpha. What is the real part of alpha? It's omega by 2 nu, which is positive. Now, you can comment on the fact that of the two homogeneous solutions that are there, which one is going to satisfy the far field boundary condition? The far field boundary condition is f as y goes to infinity will go to 0. Now, this one is an exponential which has a growing part. The first exponential is e to the power alpha y, and the real part, so you can write this as f of y as e to the power alpha real y e to the power I alpha imaginary y b e to the power minus alpha real y e to the power minus alpha imaginary I. Now, the real part of alpha is positive, which means this would be growing at infinity. This will diverge at infinity, grows at infinity. So, I can discard this solution based on my far field boundary condition. The boundary condition at infinity tells me that I cannot have that exponential. So, we are now left with a solution that is e to the power minus alpha. Alpha is omega by 2 nu 1 plus I y. The full solution u by u bar is going to be the real part of b exponential of minus omega by 2 nu 1 plus I y e to the power I omega t. Now, what should be b? F at y equals 0 is u bar. So, this is actually just u, not u bar. So, this is just u. So, f at y equals 0 is u bar, which means b is equal to if you substitute for y equal to 0, b is equal to u bar, right. So, then my u is real part of u bar exponential of minus omega by 2 nu y e to the power I omega t minus omega by 2 nu y. So, what is your final solution? So, the steady state response. Now, steady state response just means that you have waited long enough here to get this kind of a harmonic response. It is an oscillatory response that you have, is going to be u bar, sorry, it is already scaled by u bar. It is going to be exponential of minus omega by 2 nu y cos of omega t minus omega by 2 nu y. So, for that oscillating plate problem, what are you going to observe? You are going to see a solution that would appear. So, you look at the two terms. So, the first term is like an attenuation or a damping term. So there is a spatial damping that you have in the first term, that as you move away from the plate, the amplitude of your disturbance or amplitude of your fluid velocity is decreasing. But if you look at this particular term, this is like a propagating wave. So you have a term here which is omega t minus square root of omega by 2 nu y. So that's like a transverse propagating wave. Which has a frequency omega and it has a wave number which is square root of omega by 2 nu. Or if you try to calculate the wavelength would be 2 pi divided by omega by 2 nu. So there is a certain oscillatory nature of this particular solution. Okay. So you can try sketching what the solution should look like. So let's start with a time interval. So first I will do omega t equal to 0, or rather t is equal to 0. So I will sample the solution at every discrete fraction of the time period. So over one time period we will try to look at what the solution looks like. So at t equals 0, the solution is exponential of minus omega by root 2 nu y and then cos of square root omega 2 nu by y. So it will start from at time t equals 0, the plate velocity is u bar. This is basically the fluid velocity plotted as a function of y, right? So at time t equals 0, the plate velocity is u bar, because the plate velocity that I have given is u bar cos omega t. So at time t equals 0, the plate has a velocity which is u bar. So it is oscillating, that's the maximum speed which it has. So it starts with a velocity u bar. Now if you plot what is the function at this instant, the velocity is u by u bar is exponential of omega by 2 nu y cos of omega by 2 nu y. Now cos of omega by 2 nu y is going to be an oscillatory function, right? It's going to be something that is going to actually be oscillatory in nature. So it would have ideally looked something like this. This is the cosine function, how it should have looked. But it is not a cosine function because it's a cosine with a damped amplitude. So what you would observe is that it will go to 0 at the location the cosine goes to 0, but it will start to dampen out. Right? There is going to be a dampening that you are going to observe. Now if you go for the next time instant, so if you choose, let's say omega t is equal to pi by 2. So if you now say I will choose omega t to be pi by 2. What is the plate velocity? The plate velocity is u bar cos of pi by 2, which is 0. So the fluid velocity would be 0 and at the plate, and the total velocity would be, so this is omega t equals to 0. So the total fluid velocity is going to be u by u bar is exponential of minus omega by 2 nu y cos omega t, so omega t is pi by 2 minus omega by 2 nu y. Now what is cos pi by 2 minus omega square root of omega 2 nu by y? It will be a sine. So this would be a sine function. So now if I plot this, It will look something like this. And then you can now carry this on, and you can do this at omega t of 3 pi by 2. So this will be omega t of, obviously this is a little bit, there is an inconsistency here. The black line should actually, the black and the red line, oops, they should actually decrease in their amplitude. So let me just draw it in the first few halves. So and then finally, when you have omega t is equal to 2 pi, the plate velocity will be minus u bar. It will look like this. So there will be an oscillating, there is a wave that is propagating in the direction normal to the plate. That wave is attenuating, it's basically damping. It's not a wave that basically goes unchanged as it moves in the y direction. So when you have this particular horizontal motion of the plate, you have a propagating wave in the y direction. This is if omega t is, omega t is pi. Let me label them, maybe then it's, so this is omega t equal to 0. The red one is omega t equals to pi by 2. The black one is omega t equals, what was it? The blue one, right? And the black one is omega t equals 3 pi by 2. So for omega t equals to pi by 2 and 3 pi by 2, the plate velocity is 0. So the fluid velocity at the plate is 0. For omega t equals to 0, the plate velocity is 1. So fluid velocity will start from u equals to u bar. So I can write this as u by u bar if you say. So this will be plus 1, this is minus 1. Okay? Is this picture clear what is happening here in terms of the flow field that is set up? And so you can effectively see that if you are asking how much does momentum penetrate into the domain, because unlike the previous problem where you had an impulsively pulled plate problem, momentum was continuously penetrating into the plate. The distance, the viscous length scale increased as square root of nu t. So as time progressed, the region which was set into motion was constantly increasing. That's not what is happening here. Here, once you have waited long enough, you will see this kind of an oscillatory behavior, and the penetration of momentum remains fixed. It doesn't diffuse any further. So here, this distance is square root nu by omega. So there is a viscous length scale in this problem over which momentum is going to penetrate. A distance over which you will have effects of viscosity being felt in the fluid. If you think in terms of how much viscosity is actually getting how much of the viscous effects are affecting the flow, that diffusion of momentum is happening over a region which is square root of nu by omega. So this is known as the penetration depth. So when you have an oscillating boundary, let's say you have an oscillating object and you want to basically find out that this oscillating object is obviously interacting with the surrounding fluid, how much of the fluid is actually responsible for the forces that the body experiences, you already have a measure here, which is the penetration depth. Because that's the length scale over which momentum diffusion is going to happen. Beyond that, there is not anything very significant, because it's, as you can see, it is an exponential damping that is occurring. So there is a length scale in this problem which tells you the amount that momentum gets diffused. And this is something that is quite useful in a lot of different settings. Say for instance, you were looking at, so there are two side walls and there is a fluid that is there confined by these two side walls. It's like a channel. You can think of various examples. You have like an open channel. Now, if there are waves that are propagating here, so there are waves, you have excited these waves, there are waves which are propagating, which basically have a frequency that is omega. Now, if these waves are basically due to gravity, then you can actually work out what would be the wave speed. So, if there is a depth, if this is not too deep, then the wave speed will, the speed will go as root gh, and you can basically find out what would be the frequency with which it is going to move based on the wave speed. So, you can take, if the wave number is basically k, then you can find out what would be the frequency given the wave speed. But what I am trying to say here is, based on what we have done, if you want to find out that how much does viscous effects play a role, how much, if your question was, I am basically trying to study propagation of waves in a fluid. Now, the waves could be due to gravity at the interface, it could be effects of gravity because of density variations. There are various mechanisms by which you can generate waves in a fluid. Now, if you have generated waves in a fluid and you want to find out what is the amount of dissipation that is happening. Now, there is dissipation in the bulk, there is dissipation at the boundaries. Now, the dissipation in the bulk will often be characterized based on what would be a typical Reynolds number in a problem. Reynolds number would basically come about here in these kind of problems. So, if you say that the density of the fluid is rho, the characteristic speed with which motion is occurring is c, the height over which you are looking at is h and mu, something of this sort. And if you plug in values, let's say a water-like medium, and you say that I have a wave which is moving few centimeter per second over a depth that is around a meter, then rho is around 1000, mu is around 10 to the power minus 3, this is around a centimeter per second, h is around a meter. So, automatically you arrive at a Reynolds number which is very large. So, in the bulk, dissipative effects are negligible. There is not a lot of dissipation that is going on. When you are looking at a meter deep layer of water, which is basically being excited and you have waves that are propagating, the bulk dissipation is not very strong. What is strong is the dissipation or viscous effects from boundaries. And if you have to measure how much dissipation is happening from the boundaries, it's an example of an oscillating flow next to a stationary surface, which is just the opposite of what we have done. We have done an oscillating surface churning a stationary fluid. Now, the fluid could be oscillating in the far field region. So, you can think of a problem where the boundary condition at y equals to infinity, y approaching infinity, is some u bar cos omega t, and the boundary condition at the plate is 0. So, now you have this oscillatory flow that is happening, but this oscillatory flow is trying to slide over a no slip boundary, a stationary boundary. And then you can try to measure how much would be the dissipative effects in the problem. And to quantify the dissipative effects, basically you will say that there is a length scale, which is the penetration depth, that is going to scale as square root of omega by nu. So, over that distance there will be damping that will act in the problem. So, what did I write? Sorry, yeah, thank you. Yeah, nu by omega. Omega by nu has inverse length square dimension. So, nu by omega basically gives you, so this is the length over which damping is going to happen in your problem. So what you can do, obviously if you are able to solve this problem numerically with applying a no slip boundary condition on all sides, that is perfect. That basically takes care of all your problems and you are doing an exact numerical calculation of the problem. But it is also perfectly fine to solve this problem as if there is a flow, the effect of the boundary is replaced by a damping that occurs over from the side. So the side wall damping, you can measure it, the amount that it is actually affecting by this penetration depth. So this oscillatory flow example is useful in many settings where you are trying to quantify that how much viscous diffusion is occurring in a problem. Okay. So this is what we mostly had for the unsteady problem. Now, I'll just briefly talk about two variants of what we have done. So we have done this problem of a plate that is impulsively moving. We have worked this out. An infinite plate that is set into motion. Once we worked it out, we found that u is equal to u bar 1 minus error function of eta with square root of 2 by pi. Let's just make sure we have the solution written correctly. Yeah, 1 minus, no, it was just 1 minus error function of eta. So where we solved this equation, du dt is equal to no d square dy square. Now, you could also do the problem where you say that the top plate is moving with a velocity u bar and y goes to minus infinity as you go down. So, there is a top level, top of plate that you are considering and you are looking at the fluid below that particular plate. So, the only change that you would need to do is basically a change in terms of solving the problem below that region, right. So, when you are going to look at this, there will just be an 1 plus error function that will come in the calculation by taking the negative part of it. Now, let's say that instead of applying a constant impulsive velocity at the top plate, you apply a constant impulsive shear stress at the top plate, not a velocity. So, you are saying that tau, we have used sigma, right? Sigma xy is equal to x at y equals 0. So, you applied a constant shear stress at the top starting at time t equals 0. Now, if you see this equation, you can probably solve this equation, apply the boundary condition for the shear stress rather than the velocity and obtain the solution. But another way of doing this problem is if you take a dou y of the full equation, you will get dou t of dou u dou y is equal to nu dou square dou y square dou u dou y. I have taken a dou y of the full equation. Now, if I multiply both sides with mu, what is the term inside the bracket? It's the shear stress. So, the shear stress obeys the same equation as the velocity. This is now a diffusion equation for the shear stress, which has a boundary condition that at y equals 0, the shear stress is S, and at y goes to infinity, the shear stress will go to 0. So, if you solve this, borrowing the solution that we have already done, you should get this as your answer. There will be no change. because you're solving the same differential equation. You're solving exactly the same differential equation, there is no change. So what you will find right now is that the shear stress is going to diffuse into your domain, and you can work out what is the velocity that is going to be set up by this. Now, where is this of interest? Where is this kind of a problem of interest? So, this problem is of interest where you are actually thinking of this being the ocean, and there is wind that is blowing at the ocean surface. So, when there is wind that is blowing at the ocean surface, the wind is going to exert a certain stress at the ocean level. So, instead of actually solving for the atmosphere and the ocean, you can say, let me just solve for the ocean with a wind stress that is applied at the ocean air boundary. That ocean's flow is going to be generated due to this shear stress, and you can solve this. Now, in a realistic scenario, when you are thinking of an actual problem in the case of oceans, the velocity that you will observe from this will not exactly match with what you are obtaining in our problem that we are doing here, because there is a lot of other things that are going on. I mean, it depends on the scale at which you are trying to observe this particular problem. So, when we close this course, we will spend some time talking about effects of background rotation. So, I am going to revisit this problem, at least we will try revisiting this problem, exactly this problem, where there is a surface stress which is being applied. So, we are solving a problem where we are saying dou u dou t is equal to nu dou square u dou y square, which can be written also in terms of the shear stress. Now, the solution that we obtain, even though the solution is consistent with all the boundary condition, is not something that you will actually see in the real ocean application. In the real ocean application, what plays a big role is the background rotation. So, once we learn what the equations are for the background rotation, we will come back to this problem, and instead of looking at friction or viscous dissipation being balanced by unsteady momentum transport, it would be balanced by the Coriolis force. And we will see that what do the currents actually look like in the ocean, because here you are going to get a velocity profile which will be a function of depth. If so, here z is an appropriate coordinate. If I write this as z, so there will be a velocity component which will be along z, which is unidirectional. There is just a u that varies along depth. That is what you will get from the solution based on how we have done in class. So, when we eventually learn a little bit about what would be our equations of motion in a rotating background, we will take up this problem and we will see that the actual current in the ocean is not unidirectional, but it is rather spiral, which means the current is going to, so if you are looking at it from the top, let us say this is your x and this is your y. This is the direction in which you apply your shear stress. The wind is blowing, let us say, from west to east. The flow that is going to get set up will be at 45 degree on the surface. Now, you go a little further below, the angles are going to change. This is seen from the top. So, you can imagine that this is like a spiral. When you are seeing the flow, the velocity vectors are going to keep rotating and also shrinking as you keep going down. And that is what you actually observe in the real ocean, because you would not be looking at a term that comes from the unsteady effects, because unsteady effects are not so important. Rather, the Coriolis acceleration is what will balance the friction. So, we will see, if we have time, we will try to work it out. It is not a very difficult calculation, but it is something which will give you an idea regarding how the velocity field gets set up by an imposed stress. But for now, what we have managed to do in this different problems that we have attempted is to see that how unsteady diffusion of momentum plays a role in various kind of scenarios. An unbounded problem of an impulsively pulled plate, which was Stokes' first problem. Then we worked out a case of channel flow. So, we also saw this where you can think of the impulsively pulled plate problem like a mixing layer problem. So if you think of it as a diffusion of vortex sheet, then it can be viewed as a mixing layer problem, where there are two co-moving streams which are moving with different velocities. Because they are moving with different velocities, the interface is an intense region of vorticity. And you can view it as diffusion of momentum. You can also view it as diffusion of vorticity. Then we looked at the scenario where it was two plates instead of one single plate. So the diffusion of momentum gets hindered because after a time scale which goes as square root of, which goes as the height square by the kinematic viscosity, you are going to achieve the steady state problem. You will achieve a steady state profile. Then we have looked at in today's lecture, we have done the unsteady effects basically coming in when we are looking at an oscillation problem, where the plate, so this is also known as Stokes' second problem. The first problem was the impulsively pulled plate. The oscillating problem is known as the Stokes' second problem. So when you solve the second problem, we didn't focus on transients, so we ignored any transients that are there in the problem, and we directly went for the long time response. So this is the long time response. The actual solution will be this plus some transients. By transients, I mean solutions which will just die down if you wait long enough. This is what will survive. So by working this solution out, the key part that we learned here is there is something known as a penetration depth, the distance over which momentum is going to diffuse from this oscillating boundary. And that penetration depth will go as square root of nu by omega. So with all of this that we have done, we have looked at now how momentum diffusion basically occurs in time. There is a balance of your viscous force with the unsteady acceleration. Now the term that we have ignored, because we started this out by saying that there is an unsteady acceleration and then there is a convective acceleration. So the next thing that we are going to look into is the role of the convective acceleration. And once again, I will try to bring this analogy. So the reason why I did the unsteady problem first is now you will see that we have looked at equations of this kind. Now if you think of the term that we have not taken, that term looks something like this. So let's say if you look at the steady Navier-Stokes with the convective term, there will be a u dot del u term. So I've just written the term which is u dou x. Now look at these two equations. These two equations have some kind of similarity in a mathematical sense. If you write this equation down, the left hand side can be written as dou square of u square by 2 nu dou square u dou y square. It's a nonlinear differential equation. It's not a linear differential equation like the heat equation, but it is a nonlinear differential equation which still has that kind of a feature. The feature being there is a marching in space with the diffusion that is occurring, or rather the gradients in y. So earlier we did a problem where you had a time domain and there was a transverse coordinate y. So you were looking at the evolution in time for something varying spatially in y. So here, if you do a correspondence between these two equations, we are going to look at evolution in x of things varying in y. So you can already start anticipating that the flow coordinate x is going to have some correspondence to the temporal coordinate. There is some kind of an initial value problem where the initial condition is not at t equals 0, but x equals some x naught. So you are going to march. So this is basically known as equations which have parabolic character or parabolic nature. The heat equation is basically a parabolic equation. So you have an evolution in a variable or an initial value problem in a variable with boundary conditions applied in another variable. So here similarly, you are going to think of this problem, this kind of a cartoon problem that I have written down here, as an evolution in one coordinate which is x with boundary condition applied in y. So a lot of things that we have done, you can also start thinking of in terms of when you do a mapping of time with the x coordinate, the flow coordinate. That what you see happening in time when things are diffusing in time, you can now think of things are going to diffuse in space. In one particular spatial direction, there is going to be a diffusion. So this is basically one nice way to get motivated in terms of thinking of boundary layers as having something to do with unsteady flows. So we will next we'll get started with steady boundary layers.